Very good evening, everyone. Am I audible? Um, Hello, all. Am I audible to all? Okay, so did you guys try writing the insertion function? Yes, no, anything?
Are you getting my chat messages?
Yes, I am getting a chat, but not sure if I was right. I did. Okay, Kishan, was it working? Did you try it out? Yes, for BST it is working. Okay, great. So you can. Okay, so I'll quickly discuss the insertion function right now, though Kishan has done it, and then we will move ahead. Okay.
I have this question on this 444 and 2.
Four,
If
four.
that if there are three fours and one two, how will we write it in the binary search tree?
See, it depends. If you have 4 and 2, you can apply your equal to condition on either for the left hand side or for the right hand side. So let's suppose I applied it for the left hand side.
Yeah.
Okay. So if 4 is inserted initially, another 4 comes up, I'll insert it on the left, I will insert it on the left. When 2 comes up, it will compare that 2 is lesser than 4. Okay, it will go towards it left. Again, 4, 2 is lesser than that. Again, it will go toward its left. Again, it got 4. So now here it will attach itself as 2.
Okay.
Clear?
Yeah, yeah. It will be like a linked list now if it is like that.
Not exactly, but see, instead of 4, if you would have taken, let's suppose,
Or something. Yeah.
5, 5, 4, and 2. Okay. So what should I take here? And 3 also. Okay. So here you would first have 5, then again on the left 5. 4 is smaller than 5. Again, 4 is here. 2 again on the left. 3, when will it come? It will go to the left and left. Here
Right.
also, yeah, here now it will go to the right. Sorry, not right. Not here.
Oh, okay, okay, okay.
It will go in on the right hand side of 2. Clear? So it completely depends on your data.
Ma'am, can we say tree is like a doubly linked list because it has
No,
a and, uh, no.
doubly linked list don't have several nodes, right?
Okay.
So you can't say that. Though there is a program where it is like you have to convert a doubly linked list to a tree, or a tree to a doubly linked list. So there you use that property because the node structure is pretty much same, right? There you have a forward pointer pointing to the next node. You have a backward pointer pointing to the previous node. So those 2 pointers you use as left and right nodes and try to convert a doubly linked list to a tree. Clear?
Not very clear.
See, like for the node, let's suppose I am writing here class node. For that, you have 2 links, right? One link is node, you can say pointing to previous, and another link is something which is pointing to next, right? In the linked list?
Yes, yes.
Yes. So similar to that, if you notice a binary search tree, it has also 2 nodes. Instead of previous, it is left, and instead of next, it is right.
Right. Yeah.
So we use this property to convert a doubly linked list to a tree. Okay.
Okay.
So now we will move forward and we'll see the insertion function. So whenever you are inserting, you should return the starting node. Okay. So this return type should be node. Insert function. You will be given with root node. Root node, right? And a value k. So it will check if, okay, now you guys have to tell me. Yeah, this is a function for inserting a specific node, not the entire array. You can run your array in a main function and like one by one send the data over here. Clear? So if by any chance you have got root equal null, yeah, first of all, if we have to check if it is null, then what we need to do, we need to return or we need to create a new node, right? So you will write here new node and here you will be adding your data k. Clear, guys? In any case, if your given data k is less than root dot data, then you know that you have to move towards left side. So you will write here root dot left and you will call here your insert function. This time, instead of passing root, you will pass root dot left and k. Yeah, right. Otherwise, if it is less than, I will simply write else. It will also cover equal to condition. So root dot right is equals to, again, insert function. And here it will be root dot right. Clear? Anyone having any doubts? Anyone have?
Yeah, I'm thinking a little bit. So when I'm calling insert with passing k, then that is the first element.
Which
Okay.
is the first element? Yeah, it depends. No, like you have an array of elements. Let's suppose I'm giving you an array of elements as 3, 7, 6, -1, 2, and 4. Okay. These are your array elements. So you will first pass 3 as k and you will pass your root. So right now root will be null or not?
Yes.
Yes, right? So in this condition, it will be returning a new node with value k. So 3 will be returned. Clear?
Yeah.
After that, when it will traverse 7, 7 will be passed. So it will check if root is equal null. Is it null now?
No.
No. So now this time it is going to check if k is less than root dot data. So your k is 7 and your root dot data is 3. So it is not smaller, right? So it will go to the else condition and it will try to insert on the right hand side. Clear so far?
Yes.
Now when it will again call this root dot right function, root dot right, there exists nothing. Is there anything on the right hand side of 3?
No.
No. So basically it is passing null in the root dot right.
Yeah.
Yeah. So when this function will be called again, it will come here and it will see that root is equal null. Are you getting this?
No, no, no. So after 7 has been inserted.
7 is not inserted so far, right?
Okay. Oh, okay, okay.
Insert function was called, root dot right is null. So here when it will check root is equal null, this will be true.
Okay.
This time it is going to create another new node, which is 7. Clear?
Yeah.
Now this is returning. Where it is returning? It is returning to its previous function call, which was from here, right?
Yeah.
So ultimately what it is going to do, whatever your previous root was, to its right, it is going to attach this new node. Clear?
Yeah.
Is it clear?
Yeah. 100%.
After that, it is going to return root. So whatever your root here was, it is going to return that. Clear? Okay. So I guess there is no confusions in the insert function now. Yes. So can anyone tell me the complexity here? What is the complexity? What is the complexity of this function? Log n. Okay. Worst case? See, log n is the case when it's like your roots are divided. Okay. So either you will go to the left or you will go to the right. So it will be log n. This is the best case. What if your tree seems to be like this only? All the n roots are entered in on a single side. So that is a worst case. So in the worst case, its complexity is going to be order of n. Clear? These kind of trees, like where either the data is completely on the right hand side or on the left hand side, these kind of trees are known as, if it is on the right hand side, then it is known as right skewed trees. Right skewed trees. If it would have been on the left hand side, then it is known as left skewed tree. Clear?
Ma'am, if it is 100% right, then only it is called as right skewed, or it's like 50.
No, if it is 100% on the right hand side, then only they are known as the skewed trees, otherwise not.
Okay, okay.
Okay. Now, after you have inserted, there comes searching in a tree. Like, let's suppose you have to search for some number in a tree, right? So that function now we are going to write Boolean search. Search function is always going to return either true or false. So node root, you will be given a number and you need to check if it is there in your tree or not. So will anyone like to participate in here? How to write the search function? Like it's very similar to the insert function. I just want the participation from you guys.
Yeah, if no one is there, then I will.
Yeah, sure.
So, I mean, I was thinking instead of root equal to null, we'll check if k is equal to root dot data.
Okay.
Then return the root.
Return true, right? Not root.
True. Yeah.
Okay. So if by any case your k is equal root dot data, in that case, return true. What's the next scenario?
If k is less than root dot data,
Okay.
then assign root to root dot left.
If k is less than root dot data, then we need to search on the left hand side, right? So you
Yes,
can simply write here return, and you can call for the search function.
with root dot left.
Yeah, you need to go for root dot left, and k will be the same.
Mhm.
Otherwise, obviously, if there is a return function, there is no need to write else. So I
Yeah,
can write here return search
root dot right.
root dot right
K.
and k. Correct. Any other condition we are missing here?
No.
Okay. What if like there exists no tree and someone asked you to find out k? What will you return in that case? That is one condition, right? If by any chance root is equal null, then in that case you need to return false.
Yeah.
Clear? Okay. So searching, like we searched in that tree. Any other function remaining which we need to do on a binary search tree? Remove, right? That is a delete function. So deletion in a binary search tree can be little complex. So I'll just draw here a binary tree. This is a binary tree. If someone asks you to delete a leaf node, okay, this is a leaf node. This is a leaf node, like the one which has no children's. We can say it as a leaf node. So this is one condition. Other condition can be someone asks you to delete, let's suppose, let me draw tree a little more. Is it fine? Okay, so these are the leaf nodes. There can be a condition where you need to delete a parent which has single child, that is 7, or you can say 3. So that's right. And or you can be asked to delete the parent which are having the 2 children, which are like, you can say the most of the cases it is. So this can be the condition, this can be the one, this can be the one, this can be the one, and I guess this will come in the single parent condition. Clear, guys? So these three scenarios. Okay, so I'll just write here the points. One, to delete the leaf node. Next, to delete the node with one child. And next is to delete the node with two child nodes. Clear, everyone? Can anyone try to do the delete the leaf node one first point?
Ma'am, I'm just thinking that we'll traverse to that point and then mark it as node dot left equal to null or node dot right equal to null, depending on which
Yeah, it's
element.
basically like making that particular node as null.
Yeah.
Works. How will you know it is a leaf node? First, like you will be given only a number and you will be said that you have to delete this number from the binary search tree. Okay. So how will you know it is a leaf node?
By checking whether it has left and right as null, node dot left and node dot right as null. Double check.
Correct. Can you try doing the next to delete the node with one child? Okay, try it.
What I'm thinking for the second one.
Okay, so after search, once we get the node to be deleted, we'll check if any it has one child left. Like, okay. Okay. Yes, you can continue.
So my check would be either no dot left is not equal to null or no dot right is not equal to null. Then root is equal to null. So either one of them is equal to null, whatever data, and then I'm making the root as null to delete the one child node.
It's basically like you have found your node. You will check if either it has the left child or the right child, correct?
Yes.
And you will reference to that particular child. Like previously, you were making it to null. Now you have to point to that left child or the right child. Clear? I guess
Mm,
that's, yeah.
no. I didn't get it. Could you please repeat it?
I'll just write it here. See, you found out that 7 is the node that you have to delete. So now you will just point this 4 to 8. Previously, if 7 was the only child, let's suppose, you would have just made this node, like made this link as null. But now you have to link this to 8. Clear?
Okay, I was thinking that when I'm removing, the whole branch is to be removed.
Why whole branch is to be removed if one number has to be removed only though?
Okay, I was thinking like it's cutting a tree from the middle.
Nope. Next is to delete the node with two child nodes. Okay. In this case, you can see if I will delete 30, like now, if I was deleting 7, I was attaching it to 8 directly. But if I have to delete 30, which one should I attach to 15? Should it be 23 or should it be 45? 45, okay. Can't it be 21?
No, because it is further down.
Mm-hmm.
So
45, okay. If I have to delete 9, then what, which should be the node coming up over here? Is it -3 or is it should be 12?
I mean, the criteria would be which is less smaller of the two will be put, like in this case, it will be 12. And in the previous case, when I was removing 30, the more closer was 23. So that now 45 will attach to 23.
So you are saying we can make 23 as our
Correct.
main node instead of 30, right?
Yeah. Why?
Okay,
Because
okay.
I
Yeah,
mean,
say.
there are plus and minus to it. Like if I do replace with 45, then 23 and 21 will go to the left. If I make it 23, it will be more balanced.
No, it's not about balancing. It's just about having a binary tree, binary search tree. Binary search tree is not demanding the balancing. Okay. So one thing that you need to notice, you can pick the minimum from your right hand side, or you can pick the maximum from your left hand side. You can do either ways, you will be getting the correct answer. Like here, if I'll pick the maximum from the left hand side, that is 23, and I make it as the root node for this specific tree, it will be fine. In here as well, -3 and 12. From the left subtree, what should I pick up so that it should be balanced here? I should be picking 7, right? If
But
I'll be picking 7 from the left subtree, considering 9 as the root node, my tree would have been balanced, right? Yes.
yeah, but that is not the criteria. Like when I'm choosing between the left and right, is my goal towards making it more balanced or some other specific?
Your goal is to make a binary search tree. Balanced, not balanced is not your case.
Okay.
Okay.
Okay, then in that case, if I'm replacing 9 with 7, then -1 should attach to 7.
Why it should attach to 7? The remaining things will remain same. Only one thing should be gone. So either the maximum from the left subtree or the minimum from the right subtree. Clear?
No, madam. For example, when you're talking about removing underneath -3 is
Okay,
+4.
wait, I'll tell you. Let's suppose I have to remove 15. Okay, I have to remove this 15. So this is your, I'll just remove a little bit of circles. If I have to remove 15, this is my left subtree. This is your right subtree. From the left subtree, can you tell me the maximum?
Maximum is 12.
12. From the right subtree, can you tell me the minimum? Okay,
20.
21. If I will, like what I need to do, I need to remove this 12 from here and I need to replace it in this place if I'm deleting 15. This is one case. If I remove 12 from this position, is my binary tree is still a binary tree or its property is gone? It is still a binary tree, right? Yes. Instead of this, if I would have removed 45, sorry, not 45, I would have removed 21. Is my binary tree still a binary tree? Yes. So that's the thing here. If I'm removing the maximum from this left subtree, I know that the maximum is going to be the leaf node for sure on the left subtree. Yes or no? I am saying if I am picking the maximum from the left subtree, it is going to be the leaf node for sure, right or not? It's wrong, guys.
Maybe, may not be. It's,
Are you guys confused? You have to tell me the right answer. Why should I tell you?
so it depends on case to case. Like in this case, 12 is greater than 9, then I will pick 12. But if 12 is not there, then 9 would be the thing.
Let's remove 9. Now you have to remove 9 if you have to take the take the number from the left side, right?
Yeah, then 9. Then 9 will take over 21.
Yeah, right. So in this case again, why 8 will be the next max question? You are getting right? Yes. Okay, so I hope you guys understood.
Ma'am, still there is one confusion that when you had the 12, whether we should pick 12 as the replacing to 21 or 23 as replacing 21.
Which one? I didn't get you.
Yeah. So in this diagram that is there on the screen right now, um, either you could replace 21 with 9, or you could choose 23 to replace 21.
Yeah, right.
Which one and what on
It
what?
depends on you. If you are choosing the right hand side, then you should choose the minimum from the right. If you are choosing left hand side, then you should pick the maximum number from the left hand side. Like it completely depends on you.
Okay,
Clear?
so examiner will tell me whether to pick smaller from the
Which
left.
one? Who should tell? I didn't get you.
So, so the question or the examiner will tell whether it should
No,
be
no, no, no. It's completely
smaller
up
or
to you
bigger.
now. You are writing your algorithm. You can fetch it from the left hand side or from the right hand side.
Okay.
Clear?
Mhm.
Okay. So much of a discussion. I hope now you guys are clear with the deletion. See, when you have to replace with 9, again, the same concept will come, that detaching a single node, like you can say detaching a node which is having a single parent, you can say. So I guess again, it will be repeating to the second point, which is to delete the node with one child node, right? So basically, overall, we are just revolving around these 3 steps. Either it can be the first one or the second one or the third one. Clear, everyone?
Yeah,
So
so
do you want, yeah,
one second. So yeah, this is very interesting question. Like if I have to remove the 9, then I have to pick 8 to make it a balance binary search.
no,
Um,
yes, sorry, my bad. Yes.
okay. And now I'm clear.
Okay. So now, do you guys want to try this code on your own, or do you guys want me to like write the code quickly on the screen? Okay, we'll try. That's great. So now I hope that you can try your level order traversal, pre-order, post-order, in order, all the things you can execute well if you know the insertion. Oh, yeah. Sorry, Kishan, like I almost forgot that. I will share it by tomorrow for sure. Okay.
Ma'am, yesterday the code you wrote for the level order, could you please share?
I want you guys to now like write the code on your own. Okay. So the level order, you try it today on your own and see if it is getting executed or not. Clear? Okay. So I guess we are pretty much it. Then if you are done with this insertion, search and deletion function, we have few very basic questions left for the binary tree. We will finish that tomorrow. And then we will move to the questions specifically for binary search tree. Clear, everyone? Yeah, mostly questions come from binary search tree. Okay, then. So thank you for attending today's session. I will see you guys tomorrow. Bye-bye.